The last theory we need to talk about is molecular orbital theory. And here we calculate orbitals for the entire molecule instead of for individual atoms. So this is done sort of in a trial and error kind of way. You can't solve the Schrodinger equation. So they basically take an educated guess and put in a trial function and see how that works out, and then they make adjustments. And they're trying to get the lowest energy for those orbitals. Of course, like it says, we can never do better than nature at minimizing the energy of the orbital. Just before we get too far into this, the point of this is not to become proficient with molecular orbital theory. That's not going to happen. It's just too complicated. I don't really understand it myself. The point here is to understand enough of it that when the organic chemists tell us, oh yeah, that resonance is spread out over the whole molecule, they're like, yeah, I can believe that. So that's really what we're headed for. So they talk about a linear combination of atomic orbitals. There's a lot of acronyms here, LCAO. Basically, you're taking individual valence atomic orbitals from the atoms and you're adding them together. There's constructive addition and destructive. And you're going to combine all the atomic orbitals from all the atoms, whereas valence bond theory, you're only looking at combining orbitals on a single atom. And many of these combinations are delocalized over the entire molecule. They're not just localized on a single atom. So what does that look like? Well, let's think about the simplest molecule, hydrogen. So hydrogen has two hydrogen atoms that are bonded together. Each hydrogen atom has an electron in the 1s orbital. And so what we're looking at is combining these two. Remember that orbitals are like standing waves, and waves have phases. And so orbitals also have phases, positive and negative. And you can combine them in a constructive way where positive reinforces positive, or a destructive way where positive and negative sort of cancel each other out. So if we add these two in a positive way, we get this bonding orbital that gives us electron density between the two nuclei. And this is going to be lower in energy than the original atomic orbitals. This is called a sigma orbital because of its shape. So if you imagine standing at the end and looking down, it's like looking at a tube, right? Or a hot dog or something. It's cylindrical, like the letter sigma. And then we do a subscript 1s because this is the sigma orbital that's formed from 1s orbitals. If we combine those two orbitals in a negative way, which is basically subtracting them, we're going to get a higher energy orbital with no electron density here. There's a node, there's a place where there's zero electron density between the two nuclei. And so not only does this not promote bonding, it works against bonding, and so this is called an anti-bonding orbital. So this is a sigma star 1s, and this is higher in energy. Any questions so far? So whenever we add two atomic orbitals together to form molecular orbitals, we're going to get a bonding orbital and an anti-bonding orbital. Bonding orbital is lower in energy and has high electron density between. The anti-bonding orbital is higher in energy and has a region of zero electron density between the two atoms. So instead of drawing, funny balloon pictures, we draw orbital diagrams. Here, molecular orbital diagrams are a little bit different than the regular orbital diagrams. But over here on the sides, we see orbital diagrams for the individual atoms. Here's hydrogen, it has one electron in the 1s, and here's another hydrogen with one electron in the 1s. And when we combine these two 1s orbitals, we get two new orbitals. So same as with valence bond theory, the number of orbitals you end up with is the same number as you started with. You don't create or destroy orbitals. So we're starting with this orbital and that orbital, and we're going to end up with two. One is lower in energy and one is higher in energy. So these are the molecular orbitals here. And then we're going to take those valence electrons, there's a total of two of them, and we're going to put them into these orbitals following the same procedure, the same rules that we did with regular orbital diagrams. So they're going to go into the lowest energy orbital first. And then we talk about something called bond order. So it's the number of electrons in bonding orbitals minus the number of electrons in anti-bonding orbitals divided by 2. So let's look at what that is for this hydrogen molecule. So there are 2 electrons in bonding orbitals. So that's 2. And we're going to subtract the number in anti-bonding orbitals, which is 0. And that quantity divided by 2. And so that gives us a bond order of 1. If the bond order is positive, a chemical bond will form because in the process of doing that, energy is lowered, and that's going to be something that will happen. A higher bond order means the bond is stronger. If the bond order is 0 or negative, a bond will not form. So let's look at a helium molecule, right? He2. So here we have orbital diagram for a helium atom. It has 2 electrons in the 1s orbital, and here's the other one. These 1s orbitals combine, and they're going to form the same sorts of things. A bonding orbital and an anti-bonding orbital. And then as we put the electrons in, we're going to put them in the lowest energy one first. So there's 1, 2, and then we'll go to the next higher energy, 1, 2. The bond order here is different because here's the anti-bonding orbital, and here's the bonding orbital. So there's 2 electrons in each, so 2 minus 2 divided by 2 gives us a bond order of 0. So this is predicted not to happen, and it doesn't. Like, I thought helium doesn't make compounds or molecules. It doesn't. It doesn't. We can also look at some really kind of weird ions. So an He2 plus ion. So what would that be? Well, it's 2 helium atoms, right? And it's missing an electron. So that means that one of them must be a positive 1 ion. The molecular orbitals are going to be the same. It's just that we have a different number of electrons. So we put them in 1, 2, 3, and this bond order is going to be 2 in the bonding orbital minus 1 in the anti-bonding orbital divided by 2, which is a bond order of 1/2. So it's predicted that this ion exists, and it does. It's just not common at all. So this is sort of summarizing what we talked about so far. We are approximating molecular orbitals as linear combinations of atomic orbitals. The number of molecular orbitals is equal to the number of atomic orbitals that you started with. Whenever you combine 2 atomic orbitals, you're going to get one molecular orbital that's lower in energy, the bonding orbital, and one that's higher on anti-bonding. When assigning electrons, we're going to do the same thing as we did before. Fill the lowest energy orbitals first with up to 2 spin-paired electrons. We're going to follow Hund's rule when filling molecular orbitals of the same energy. So that's the electron comes into the hotel and it's going into a room that has 3 beds, and there's a guy in one bed. He's going to take his own bed, right? He's not going to cozy up with this guy he doesn't know unless he absolutely has to. And then stable bonds require a positive bond order. So, use molecular orbital theory to predict the bond order in H2+. Is the H2+ bond stronger or weaker than the H2 bond? So, good news for you, I'm not going to make you draw molecular orbital diagrams. They'll be given to you on an exam, and you just need to be able to fill them in. So this would be the atomic orbitals, orbital molecular orbitals. So this is 1s, and this is 1s, and this is sigma 1s, and sigma star 1s. And then we often show where those came from. So if we have an He2+, that means we've got two hydrogen atoms, but one of them has a positive charge. It doesn't matter if you put it on the right or the left. So this hydrogen, regular hydrogen, has one electron, and hydrogen ion has no electrons, right? So it has no electron here. So we've just got one electron. We go to put it in the molecular orbitals. It's going to go down there. So what's the bond order? Well, the bond order is the number of electrons in bonding orbitals, 1, minus the number in antibonding orbitals, 0, divided by 2. So this is a bond order of 1/2. Is this bond stronger or weaker than an H2 bond? It's going to be weaker. In the H2 bond, we have 2 electrons here, right? And the bond order 2 minus 0 over 2 is 1. The bond order is higher in H2 than in H2+. So H2 is going to be weaker than H2+. Any questions? So we are only going to be talking about diatomic molecules, 2 atoms, because that's as simple as you can get. And first we'll talk about homonuclear diatomic molecules. So the molecule is 2 atoms of the same element. So H2, He2, those are homonuclear diatomic molecules. So if we go into the second period, we come to lithium. And here's lithium's valence electron, and this is lithium's valence electron over here. These are 2s orbitals. The 2s orbitals combine just like 1s orbitals do, and they form a sigma 2s and a sigma star 2s. One bonding, one antibonding. We got 2 electrons. We put the 2 electrons in here, and we've got 2 minus 0 over 2. So we've got a bond order of 1. This is so exciting. If we look at beryllium-2, so Be has 2 valence electrons. This is a lot like helium. And we're going to get, of our 4 electrons, there'll be 2 down here and 2 up there, and the bond order is going to be 0. Number of bonding electrons minus antibonding, 2 minus 2, 0. And divide by 2, and it's still 0. When we get to boron, now we have to think about the p orbitals. So how do p orbitals combine? Well, p orbitals are along the x, y, z axes in 3-dimensional space. And so if we look at the one that's along the x-axis, these are going to be parallel to each other. And so we can add them in a constructive way, which will cause the bonding orbital lower in energy, large electron density between the nuclei. Or we can look at destructive interference, essentially subtracting them, and then we get a node between the nuclei, and the electron density is actually away from that bond. So these are also sigma orbitals, because if you look at it from the end, it's cylindrical, right? just like the letter sigma. So this is sigma 2 pi, because it's made from 2 pi orbitals. Sorry, 2p orbitals. And sigma star 2p. And then we have two more orbitals. So here's py. And so these guys can't overlap end to end, right? So they're going to do the side-to-side thing, kind of like in valence bond theory. And so if we add them together, so the positives and the negatives are on top of each other, we get something like this, where again we've got a lot of electron density between the two nuclei. Negative, the destructive interference, we get something like this. And so this is a pi orbital, like the pi bonds we saw in valence bond theory. So this is pi 2p and pi star 2p. And then there's one more. We've got the PZs. So again, these are going to make a bonding and an anti-bonding orbital. Here we're just looking at it from the top instead of from the side. In this one, we're kind of looking at it from the side. Here we're looking at it from the top. And again, this is also labeled pi 2p, and this is pi star 2p. So these pi orbitals have the same energy as each other, but they have a different energy than the sigma. So the relative energy ordering for the molecular orbitals that we get from the 2p atomic orbital combinations isn't the same for all the molecules. It has to be determined computationally, and we're not going to make a big deal out of this. But boron, carbon, and nitrogen have a different order than oxygen, fluorine, and neon. And so if we look at it like this, the two s orbitals and what they do is the same. And here's our 2p orbitals. This is what most molecules will do. So the sigma is the lowest, and the sigma star is the highest. And then pi and pi star are in the middle. Boron, carbon, and nitrogen, which, you could, first letters, and be careful now, they're going to switch the order of these two. And there's no answer to why, they just do. So on an exam, I will give you a diagram like this and ask you to find the bond order for nitrogen 2 or something. And I won't try to trick you by giving the wrong diagram. I'll give you the correct diagram for the molecule that you're doing. But we do have to know about this for the homework. So this is the attempt to explain why the order is different. Okay. So this would represent the molecular orbitals. We're not showing all the atomic orbitals for boron 2, carbon 2, nitrogen 2, oxygen 2, fluorine 2, and neon 2. So we see that the order of these switches between nitrogen and oxygen. So as we go across, basically what we're doing is we're adding one more electron, right? So one more electron from each atom, so adding a pair of electrons. So here, now we're going to have 2 electrons in the pi bonding and 2 electrons in the sigma bonding and 2 anti-bonding here. And so this is also going to give us a bond order of 1. Here we're adding 2 more electrons. Those both go into a bonding. And so this gets a bond order of 2. Here we're also adding electrons into a bonding orbital. So this goes up to 3. When we get over to oxygen now, the next 2 electrons that are added go into an anti-bonding orbital, and so that's going to cause the bond order to come down. So the bond order here is 2, and for fluorine it's 1, and then for neon 2 it's 0, because neon 2 doesn't do that. And we can look at the bond energies and the length, and we see that as the bond order increases, the energy, the strength of the bond increases, and the length of the bond decreases, gets smaller. So we know from experiment that oxygen is paramagnetic, which means it's attracted to a magnetic field. For something to be paramagnetic, it has to have unpaired electrons. And the Lewis model and valence bond theory can't do this. So here's Lewis theory, the Lewis model for oxygen, O2. Looks to me like all the electrons are paired up, yeah? And here would be the valence bond theory, where we've got a sigma bond here, and this is a pi bond, and then we've got lone pairs. But again, everything's paired up. So why would oxygen be attracted to a magnetic field? Well, if we look at molecular orbital theory, here's oxygen, look at that. We have 2 unpaired electrons. Oops. Okay.
Pampers Cruisers 360 for up to 100% leak-free fit.
Because that's
Live
relevant.
wild and free.
If you want to be healthier, you've got to get Kachava.
I started Kachava a month ago because...
Good grief.
So, we're going to take this oxygen gas, pass it through this copper coil that's immersed in liquid nitrogen. The liquid nitrogen will condense the oxygen into liquid oxygen, which will collect here in this pre-cooled door. We will then take the liquid nitrogen and pour it between the poles of this magnet. We'll pass the oxygen also, pour it through the poles of the magnet. Then we're going to see if there's any difference between liquid nitrogen and liquid oxygen.
Why do you look like James?
Pardon me?
It looks like James Mason Top Gear.
I don't know. So I was turning on the oxygen gas. And that's liquid oxygen. Takes a while.
Very
Very
cold.
cold. Very, very cold. So there you go. Liquid oxygen has a slight blue color. So this is the nitrogen. And that's kind of what you would expect if you pour water over a magnet, right? It's just going to go through. That's different. That's a really strong magnet. The liquid oxygen is attracted to the magnetic field, and so it's sticking there between the magnets. It's actually extremely cold, not just super cool.
Yeah, the fact that he's not wearing a lab coat is
A lab coat wouldn't really help. No.
well, if you pour liquid nitrogen on your arm, isn't that gonna hurt?
Yeah, if it's on the, if your lab coat's there, it's still gonna hurt. Yeah.
Oh my God.
So, any questions? So this is molecular orbital diagram for nitrogen, and we see that nitrogen does not have any unpaired electrons. If these two were switched in order, if this was lower like it is over here, then nitrogen would have unpaired electrons and oxygen would not. So oxygen has the unpaired electrons, it will be attracted to the magnetic field. Nitrogen is not attracted. Okay, draw a molecular orbital energy diagram and determine the bond order for the N2 plus ion. Do we expect this bond to be stronger or weaker than N2? And is N2 plus diamagnetic or paramagnetic? So instead of watching me try to draw orbital diagrams, we're just going to use these, okay? So we're doing nitrogen, so we need to use the one over here. So the most important thing is getting the number of valence electrons correct. So we're doing N2 plus. So we have 2 nitrogens, and they each have 5 valence electrons, right? And then if we have a positive charge, that means we're missing an electron. So we need to subtract 1, and we have 9 valence electrons. You can put them into the atomic orbitals if you want to, but there's really no need to do that. So I'm going to take my 9 electrons and I'm going to put them into the molecular orbitals up the middle here. So we start at the lowest energy. There's 1, 2, 3, 4, 5, 6. He's going to take his own orbital because he can. 7, 8, 9. So calculating bond order, these are bonding orbitals, and this is an anti-bonding orbital. So in the bonding orbitals, 2, 4, 6, 7 electrons, and in the anti-bonding orbitals, 2 electrons divided by 2. So that's 5 halves, or 2.5. Well, what's the bond order of N2? It's got 1 more electron. So this is going to be 8. We're going to end up with a bond order of 3. We can also see that if we go over here. There we've got our bond order of 3. So going back to this has a bond order of 2.5. N2 has a bond order of 3. Which bond is stronger? The N2. N2 plus has a weaker bond. Is this thing going to be diamagnetic or paramagnetic? I got those mixed up again. Okay, so the prefix di means 2, right? Para sounds like you're saying pair of, but that's not what it is. It's P-A-R, not P-A-I-R. But di means 2. 2 by 2, the animals went into Noah's Ark. And so if it's diamagnetic, everybody has a partner. Everyone's paired up. This guy doesn't have a partner. So this is going to be paramagnetic. So it should interact with the magnetic field. Any questions? Now we're going to look at heteronuclear diatomic molecules. So here we have 2 atoms that are of different elements. So this is the MO diagram for no. Oxygen is more electronegative, and so its atomic orbitals are a little bit lower in energy than nitrogen's. But the S's are going to combine to form sigma and sigma star. The P's are going to form sigma, pi, pi star, and sigma star. Okay? And then if we look at the electrons, nitrogen has 5 electrons, valence electrons, oxygen has 6. And so we've got 2, 4, 6, 8, 10, 11, total of 11 valence electrons in there. So, you could calculate the bond order and compare it to something. This is kind of weird. Fluorine is so electronegative that all of its orbitals are lower in energy than hydrogen's 1s atomic orbital. So fluorine has electrons in the 2p sublevel, but those are lower in energy than hydrogen's 1s electron. It's kind of crazy. So when these combine, it's a little bit different. So we've got this s orbital combining with one of the p orbitals to make a sigma and a sigma star. And then the other 2 p orbitals have nothing to interact with, and so they're just going to stay the same. And I'm just going to skip that one. Okay. So we've talked about ozone before and how the Lewis structure is tricky, right? Because it has this resonance, and so the correct structure is actually a combination of these two, a hybrid. We know from experimental information that this bond and that bond are identical, the same length, the same strength. But here in the Lewis model, we have a double and a single. They're obviously different. Here's the valence bond model. And also, we've got a double bond on one and a single bond on the other. They're different. So neither of these models helps us to understand the structure of ozone. But in molecular orbital theory, now see, this is 3 atoms, and that gets more complicated, so we're not really going there. But we have seen how the atomic orbitals combine into molecular orbitals. And so now that extra bond that we were having to assign as a double to one side or the other can be spread out over the entire molecule. And we can see that this bond and that bond are identical in length and strength because the electrons are spread out over the entire molecule. And this is the big one for OChem. OChem does a lot with resonance structures because when you have resonance, it stabilizes the molecule, and so that affects its reactivity and all kinds of things. So this is the benzene molecule. It's a 6-membered carbon ring, and in the Lewis structure, we draw it with alternating double and single bonds. And so we have the 2 resonance structures where the double bond is just shifted to a different position. So neither of those really describes what's going on. That second bond here, here, and here are not localized between 2 atoms. They're actually spread out over the entire molecule. And so it uses a molecular orbital. All of these carbons are identical, and benzene is symmetrical. Any questions?